We'll call this object A. All right. Now we do a force diagram, we talk about all the different forces acting on object A. So let's say object A has a rocket right here shooting out. Well, now we have a force pushing object A this way, and we'll call that force rocket. Okay?
I already disagree.
Okay. How do you disagree?
Because it should be going all directions.
All directions? The rocket's only pushing in that direction.
How so?
So if the rocket is on this side and it's shooting stuff out this way, it's pushing in one direction. Same thing if you launch like a model rocket up in the air, right?
Okay, I got you.
The force is going in one way.
Okay.
Now
I was thinking already a non-vacuum environment.
Right. Well, even in a non-vacuum environment, in any environment. So if you want to say, then we're going to add things like air resistance, you would then do this. So now you have, and that's a good point, you have air resistance going this way. Now, obviously, if it's going forward, it's got to be smaller than the force of the rocket, right? So we'll call that air resistance, and see how that line is shorter than this line? So that's how basic force diagrams work, is the length of the line is going to be equivalent to the force, the relative force of it.
Yeah,
so this
smaller.
rocket, yeah, exactly. So this rocket is here. In the case of doing this on a horizontal plane, if this is the ground, then we would also say you have gravity working on it, and eventually it'll drag it down. Now, when we were talking about in your model, you have object, and we'll just for convenience sake, we'll call this object B. You were saying that you don't have gravity in your model.
Yeah.
You have density, which is a quality of matter. So that's not a force.
Okay, sure.
Density is just the compaction, how compact the molecules or atoms, depending on what you're describing, are of the particular substance, right? So that's density. So density isn't a force. What is the force that pulls this object towards the ground here? So what's this, the G? That's in my model.
Yeah, that's its own weight.
But weight isn't a force either. So weight is a quality that mass has.
Why does it have to be a force, though? Why are you so obsessed about it being a force?
Because all objects...
Because gravity isn't a force either, by the way.
Gravity's
No, it's not.
Yeah. In fact, it's one of the four fundamental forces.
No,
so we have...
I know you're going to say it's the weakest, but I'm saying that I already know it's the weakest of the four fundamental forces, but it's non-existent. It's omitted.
So
it's
what force is bringing something to the ground?
Well, this is dense.
Yes.
So it has mass and it's dense. And I don't know the difference between density and weight, because to me they seem virtually the same.
Well, think about it this way. Here's a good example of what the difference would be. So weight is mass times the gravitational force.
Hold on, you're telling me the difference between density and weight.
Yes,
I need to... Okay.
So if you imagine weight being mass times the gravitational force, that gives you your weight, which is the quality of that particular matter. Density is the quality of its actual physical structure, so it's how close the particulate matter molecules or atoms of that thing are. So something can be very dense, but if it happens to be light, it can also not weigh a lot. And density is usually associated with weight, especially depending on what kind of density you're talking about. But not always.
See, now I got it, because now you're helping me distinguish the difference between density and weight, because certain different densities determine the weight. Like
most of the time, yes. But for instance, you could have a very dense styrofoam ball, right? A styrofoam ball can be quite dense, but it's also usually pretty light. You could take a less dense piece of...
Well, it still would have, it would be technically dense, but and it doesn't have weight. But it's, well, I don't under...
Yeah, like a styrofoam ball can be quite dense. Now, it depends on what quality of density you're looking at. Are you looking at atomic density, molecular density? What are you actually looking at? Because the individual elements of that styrofoam have air in between, which gives it its lightness, right?
But you have to realize that there is no gravitational forces in my model.
Right, so what I'm asking is what's pulling it down?
I don't understand, like, why isn't density and weight a good answer? Like, that is pulling it down. Its own density and own weight is pulling it down.
No, because
that's what exists in my model.
Neither of those are forces. So every object will stay at rest.
I don't understand, like, why wouldn't or why does it need to be a force? I don't understand that obsession.
Because every object will stay at rest until a force is applied to it. So an object can't move or have any kind of movement to it until a force is applied.
Okay.
And so you have to...
I got that.
So without a force, that object wouldn't fall.
Without a force, that object...
For the same reason, like this car won't go, right? Without the force of the motor pushing it. So, it won't just sporadically like fly up in the air, right?
Where are you confused about? Because I'm following. Without a force, that wouldn't fall.
Right.
I got you.
So what is the force, if it's not gravity, that will make that thing fall?
Now you have to explain, and do not say, because it's not a force, why density and weight is an appropriate answer.
For the same reason blue or green isn't an appropriate answer, because neither of those are forces. So neither of those would cause that thing to fall. The fact that this object could be blue or green wouldn't make it fall to the ground. Same thing is true of its density or its weight, because density or weight are just qualities of that matter. It's not going to apply a force, which you would need to actually physically move that thing.
Yeah, well, I agree with you that you need force to move the object.
Yeah.
But, I mean, it has a weight. Could you agree on that?
Yes.
So, its weight is bringing it down.
It has a mass.
So when I throw a football into the air, like, what goes up must come down. So
but that's only with the gravity model.
The weight and the density of the football is going to bring it back down.
But weight is dependent on gravity. So
the force is me throwing it, and its own weight and density will bring it back down.
But weight is dependent. Weight is dependent on gravity. So without that, it wouldn't fall.
And that's where we have a fundamental disagreement. I just totally reversed it and explained it in a more practical manner.
Here's an interesting thought experiment. Obviously, you don't believe in space travel, right?
No, I don't.
Okay, but do you believe in the airplanes that can mimic zero-G gravity by going into free fall?
Well, yeah.
Okay, so imagine you're in one of those zero-G.
How do you create a zero-G environment inside of a
plane? You just go to free fall.
No. I understand how you just go like that, and in that 10-minute little span right there that you have. That's your weightlessness. That's zero-G. I understand that, but I'm just thinking we're in a zero-G, and they say that we're contained in the environment, which is why we can have a zero-G inside of the zero-G. And what interests me is that where we have the closed system, so that would be non-vacuum, and then the vacuum. So where does the closed system, which is the non-vacuum, meet the open system, which is the vacuum?
Well, that's actually a fairly good question. It's not a definitive line. You get less and less air density as you go up higher and higher, which is why it's really hard to take a plane super high, because as you get higher and higher, it takes more and more energy to get up higher and higher. So you're basically thinning out. That's why the oxygen is way thicker down at sea level. So we talk about everything changes at sea level. The boiling point at sea level is different than it's going to be up in the Colorado Rockies, because the air is far less dense up there.
Yeah, I know. I just really want to know exactly to the inch where that little magical pop out barrier.
There is a magical. It's like it's the.
Because we're in the non-vacuum.
Right.
And then we go pop, and then. So, but
it's more like a thinning.
I understand the gradual thinning, but if there is a gradual thinning, there has to be a definitive barrier.
I mean, it just depends where you want to mark your line. Like, do you want to say this many atoms of air or molecules per air per cubic meter equals space? It's a nebulous concept. It's really just a gradient. It's like anything else.
I want to see
where it's like saying where's the difference between blue and green.
I want to see that,
because blue and green share wavelengths. Blue and green are just different wavelengths of light, right? We have this color we call blue. We have another color we call green. Yeah, there's a bunch of stuff in the middle where
they go at different wavelengths.
Yeah, and there's a bunch of stuff in the middle where you and I could look at this thing and say that's blue or that's green, and we wouldn't be able to tell, because it's just so close to the middle we wouldn't know. right? It's the same thing. It's a gradient that goes from one to another. Now,
I see what you're saying.
There could be one part where you go, I am insisting this is blue. I can tell, and I'm like, I'm insisting this is green. And to be honest, neither of us are right or wrong on that, because we're both on this gradient and it could be either one. It's the same thing with that. It's a gradient out there, and if you said, here is my definitive line of when we hit space, when we hit that vacuum, then whenever you draw that line, you can find that altitude, you know, and it doesn't matter kind of necessarily where that is.
So my answer with why that this force is thrusting this object, and its own density and weight, well, it's not a good enough answer. So I have to work on a better answer.
Or you have to think of what weight is, because we understand weight as mass times gravity.
No, I gave a more practical answer, or what's it called?
Definition?
Comparison with throwing the football, because I forced the football up, and then so its own weight and density will bring it back down, which is exactly
what do you think weight is?
Well,
because in the physics model,
I guess it's the weight would be.
In the physics model, weight is mass times gravity.
The weight would be the quality of the density, then, based on what we just talked about. How whatever the object's density, that would determine the weight.
But then what happens with those objects that have a high density but lower weight than other objects with a lower density?
What do you mean what happens then?
So if weight is completely dependent on density, what about objects?
I didn't say that.
No?
No.
Okay, I misunderstood you. So just explain again what weight is.
Explain what weight is?
Yeah.
Well, I guess like I just said, I just said it literally. Like, do you want me to repeat it very verbatim? It's based on the object's density, that would determine its weight. I mean, I'm 170 or 80 pounds. You know, that's weight.
But in that model, the model that you're using,
that's like a mass,
right?
An object, and it has a weight, and
but but objects have different weights. The same object has a different weight depending on its gravitational.
So I guess by that, it's still density is weight. I mean, that's density. That's how I actually do mine is this. There's G, gravity, equals density, weight.
Divided by weight?
And no. It's everything that gravity describes in the heliocentric model, density, weight, and buoyancy describes in the flat Earth model.
Well, the problem is both buoyancy and weight are dependent on gravity.
This is how I. Well, I know that's what you think, but mine is just this.
But that's fine. So what I'm saying is we have to redefine what weight and buoyancy are, because weight and buoyancy.
And that's why I have a distinct barrier between it, because I have this. That's density. It is weight. Oh, okay. So that's why the G is there, because anything that the gravity can describe. Oh yeah, like I said, that's the opposite. These are density is what makes the car keys fall to the ground and land on the floor.
Well, density is just the quality of it. Density is just how close the molecules are. So it's not a force. That's just a quality, just like blue, green, or
okay. Density isn't a force. Okay.
Right.
Cool.
So it can't fall.
Well, but if it's in the air, it's going to fall. It's not going to stay. What's
going to make it fall?
Oh, well, I guess what's going to make it fall, to give you an even better answer, is the lack of density here. There's
the same lack of density here. Why doesn't it fall up?
Well, because it's dense. You drop. It's not made of helium. If you drop,
there's no force. So
hold on. If you drop if you let go of a balloon, well, depending on what's inside of it, it's going to go up.
Let's stick to this answer. So
hold on. The rocket is dense. So the helium balloon is going to go up because it has less density. This rocket is going to go down because it has density.
But density is not a force. So this thing cannot move until a force is applied to it. So what is the force that's going to draw it down?
What are you talking? Density cannot move unless a force is applied to it.
No,
yes.
Objects can't move until a force is applied to them.
Okay. We already.
So an object in motion stays in motion, an object at rest stays at rest.
Okay.
Without any outside forces. So density isn't a force. You already agreed to that. So density can't cause this to move.
And I'm going to look into that because I'm just fucking agreeing with you.
That's fine.
Just move on to the next one.
Yeah, please do. So if density is not a force.
Because I'm still, you really haven't made any like good points. You just keep repeating yourself on.
Well,
you keep saying density is not a force.
Which it is.
But I not only have I explained with the football model why the football falls because of its density and weight. Now I've further explained why because it falls because there's air here, so it's obviously
there's air here. Why isn't it falling this way?
Because it's made of fucking steel, man. Steel doesn't float.
Without any force applied to it,
steel doesn't float, dude.
I think this is what you're misunderstanding. So in this model, in our typical model, we have a gravitational pull that's coming from the Earth. That is
I understand. That's in your model, but in my model it's different.
The density of this is the same as the density of this, relatively. In fact, this is less. Well, if anything, it should be floating up. But without the pull of gravity,
steel rockets float up.
Without the gravity pulling it down,
understand that.
What is pulling it down?
I gave two answers now.
You keep saying density, which is not a force.
No, not only have I said density and its own density and weight pull it down, the lack of density here, there's air in between.
There's
of course,
air up here.
No shit.
So if there's no force,
so there's air up here. Why doesn't it float?
Because of gravity.
Because of gravity. So
without gravity, it wouldn't go down.
Because of gravity.
Yes.
Come on, man.
Yes. That's the force.
Okay, well, this is you.
So here is what I'm asking.
Gravity is the force.
Yes.
Okay.
You find a force diagram which will explain why your objects fall down, what force is applying to them, and what falls down. And we have plenty of weeks to do this. Like you said, you're going to be around town for a little bit longer, so you have plenty of time.
I find it very surprising that you don't understand that steel doesn't float.
Without gravity, steel would float just like anything else. There's no reason for steel to fall. Steel doesn't have some intrinsic property to go towards the ground.
The only time steel floats is when it's on top of a fucking sea. It's floating because it's dense. It's a buoyancy. It's keeping it afloat.
Or in outer space.
See how I don't need to use gravity. I can. The steel is floating on top of the fucking
but you're still
oceans because no, I'm using buoyancy.
Buoyancy is gravity. Buoyancy.
No, it isn't.
The equation for buoyancy is gravity.
No, the reason the ship is floating is because of its buoyancy, which is the opposite of density.
It's not density.
There's no need for gravity.
Density is a scale. There's no opposite to density. Density is a scale. Something's less dense or more dense. They can't have the opposite of density. Buoyancy.
Density. So density is a force then?
No.
Yes, it is.
It's a scale.
So you taught me something today.
It's like blue and green.
Density is a force here.
No.
Well, you say what is the force that is bringing it down?
Yeah.
Well, it's density is bringing it down.
That's a force.
Then by that definition, density is a force.
It's not a force.
So thank you. You do help,
but it's not a force. So
you just enlightened me. Now I
guess. I mean, you could keep saying that, but so you used to.
Gravity isn't a force, and density is a force now.
Gravity is one of the four fundamental forces. So buoyancy is part of gravity. Without gravity,
there's no
buoyancy.
Weak force, the electromagnetic, and then gravity.
Yeah. Without gravity, there's no buoyancy. So buoyancy is just a product of gravity. If you have water,
I wish you could have a picture of gravity.
If you have water here, well, we actually can take some pretty interesting pictures of gravity, especially during eclipses. If we have water here,
there's eclipse coming up here too.
Yeah, I know. If we have,
I know you've been thinking about it too.
Oh yeah. Well, I mean, I don't.
Have you gotten? Have people like just complained to you in general about like, hey, are you still getting any messages about?
Oh yeah, absolutely.
Oh, okay, cool.
Daily. So if you imagine this as water,
and who are the people daily messaging you who are concerned about the globe Earth versus the flat Earth?
I mean,
this interests me now.
It depends who you're talking about. So some people, like I said, they have some issues with some of your transgender stuff. I got those. I texted you when I got that message asking if you wanted to talk about it. Some people are discovering the debate as it goes on, because that's what happens with podcasts. People don't. It's not like TV. People don't just watch it when it comes out. They usually watch it over or listen to it over the span of a few months. So I will probably keep getting messages. And when I say daily, I'm exaggerating. We probably got like 20, 30 messages the first day, 40 or 50 the next, and then it started dwindling down. And now I probably got 7 or 8 this week.
Still, it's awesome though.
But anyway,
I mean, you got some good reviews, right?
Oh yeah. I mean, people are interested.
I mean, I don't give a shit if people think I did a terrible job. Like I do not care at all.
Right. But anyway, let's say buoyancy real quick. So let's say we have a ball here, right? And this ball has air in it. And it's floating in water. Now, what causes it to float in water, the buoyancy, is actually a product of gravity.
No.
So what's going on is...
I understand displacement of the force. Right. I understand.
So if what's in here is lighter than the water around it, it floats.
Dude,
and the reason that it floats...
You're describing something to me that I already know. Like, I already know
how...
If
you know that, then how do you explain buoyancy without gravity?
How do I explain buoyancy without gravity? Well, you place this, and this is dense, and it has a weight. And so you're placing it in the water. So it obviously is the buoyant force of this is obviously floating. So you're placing it in there, and then that's the displacement. You're placing it in the water. So obviously it has to do some equal and opposite thing here, and that is the buoyant force is the equal and opposite reaction to what happens when you place it in there. There's a displacement of the water.
Equal and opposite to what?
Whatever the density and weight is that you put into it.
So this
whole thing could be full of different objects that are floating in different levels.
Here's the buoyancy force, and in my model, actually because this would be shorter because the buoyancy is holding it up, here would be the gravitational force. What is that force in your model? You just said it was equal and opposite going up.
Yeah, that right there is buoyancy.
Buoyancy is going up, not down.
Yeah, in your model.
So buoyancy is going down and up?
No. Buoyancy is
pulling it down into the water.
It's weight and density.
Weight is mass times gravity. So what is weight in your model?
So weight in your model is mass times gravity.
Yeah.
And that attracts objects what is it? It doesn't depend on it. Doesn't matter. Depending on the mass, doesn't matter. And all objects are being pulled equally towards one another.
Yes.
It's crazy. Like,
I'm not sure.
First off, people in general don't even they don't even understand the heliocentric explanation of gravity. I just explained it and he agreed, and I just disagree with it. It's ridiculous to me.
But you haven't proposed an alternative. So you
I have
what weight is.
You just disagree with it.
What's weight then?
It's obviously the mass of the object.
Okay. So if it's the mass of an object, that's also not a force. So still that can't be pulling it down towards the ground. And you have to determine why that direction. Why is the direction towards the ground in your model? You're saying because it's steel, because it has weight. That only works if you have a force pulling in a specific direction. In your model, if there is no gravity, there's no reason that things shouldn't go up into the air or off to the side. What is the force that's pulling it towards specifically the ground?
What is the force that's pulling what specifically towards
anything? Any object, any piece of mass that you're dropping right here. Why is it that it's going to fall towards the ground?
It's not. It's because you held it in the air.
Okay.
But
again,
why? If gravity is real, why wouldn't I jump and then stay in orbit and then start?
Gravity pulls you back.
Orbiting around the Earth myself.
Because gravity pulls you back down.
Are
you asking why you don't go into orbit?
Yeah.
If we put you high enough, you would. So, and essentially what an orbit is an object that's continuously falling. If you are high up here, and you're an object, you're being locked in by gravity, and you're continuously falling down. And as you fall, you're circling this guy, and you're locked. In that orbit. Now, if we get you, it doesn't matter if that's a satellite or you, a person, we can put you up there, and you would do the exact same thing. with the right lateral momentum, you would do the exact same thing.
Well, I need to do a GoFundMe to get
Well, you wouldn't even need to do that. And here's a few things that I'm suggesting, because we briefly brought this up when we were down there. But one of the questions that I would have for you that has to that we talked a little bit about, but unfortunately there was some loud audience members and we didn't get to talk about it enough, which is our perspective of the stars in the sky when we look in the northern hemisphere and we look at a time lapse, or just lay on your back and watch the stars at night. You'll see something that looks like this, and all these streaks are stars as we're looking up and the thing is spinning. Now,
well, if that's the North Star,
yes,
yeah.
Exactly. Now, what a lot of people don't understand is this is going to be the same in the flat Earth model or the heliocentric model. It doesn't matter. The spherical Earth model, they're going to see the same thing for this. The difference is,
I disagreed with that. Remember, because all the different directions that are going.
Oh, you believe? I understand what you're saying. That has to do with the parallax issue.
Yeah.
It is.
So I mean, that would be fucking crazy. That would be all wiggly wobbly, all that shit.
Well, no. In your flat Earth model, you would still see this.
Oh yeah, of course.
Okay, correct.
But not in the. You say you see it in the heliocentric, but that's, in my opinion, that's impossible, because in your fucking model, this shit's all flying all over.
If it was anywhere near us, you are correct. Unfortunately, because it is so far away, that distance is so small, and we do see those little wiggles. They're just so hard to capture with standard technology. You can see it if you have a good enough telescope. But here is the main problem I have. If you are looking,
you just gave me an idea. We should go to fucking an observatory together.
Yeah, we can go to Palomar.
We should do that.
If you are looking at
what is it? I mean, is that a San Diego observatory?
Yeah.
I've never been to one here. I've just gone to the NASA. They have a NASA like dinosaur thing, and they have
NASA dinosaur.
They had they had some fucking, where was it? No, it's not La Jolla. The fuck is it? Dude, where the fuck is it? I don't know. It was a freaking It was something. It was somewhere around here. Oh, it was a museum. It was it had like a fucking little duck pond.
Are you thinking? There's two across from each other. There's the Reuben H. Fleet Science Museum, and then there's the Natural History Museum.
Okay. All right. Well, it was one of those.
Okay. But, so here's my question. This is what we see in the northern hemisphere. However, in your model, in the southern hemisphere, if we were in, let's say, Argentina or Chile, and we were looking south, we would see, because you imagine